We'd already discussed that when light travels through a different material or medium, it's going to bend if that material is transparent. And so as the light goes through some glass, it's going to refract or bend. And we can use this to make lenses. Of course, a common application of lenses for eyeglasses. The type of lens we're going to focus on is a double convex lens. This is going to be a lens that's thicker in the center and tapered off to a point on either side. We need to assume that the index of refraction of the lens is greater than air, which is 1 for our purposes. So it's typically made of glass. It might be made of plastic as well. For a double convex lens, all incoming light that is parallel to itself, like from the sun, from a faraway source, is going to then be bent and focused onto a central location. We call the distance from the center of the lens, and all distances are measured from the center of the lens, the distance from the center of the lens to that spot is called the focal length. And that spot itself is called the focal point. So for a double convex lens, the lens will be thicker in the center and then tapered on the outsides, and this will converge the lights onto a central location. So we call it a converging lens. Now, just to give you an idea of the opposite of that, we could have a diverging lens, which is thinner in the middle. And so for a diverging lens, all light that's coming in that's parallel, like from a faraway distance, is going to go away from a focal point. So if we follow the rays backwards, we see that it looks like it originates from one spot. So they do have a focal length as well. They do have a focal point as well, but it would be on the opposite side of the lens. It's going to go away from that focal point. We also have stated that the focal point is the same on both sides, so that means that whether the light comes from the left, it'll focus on a certain point, or if the light comes from the right, it'll also focus on a point that is the same distance from the center of the lens itself. So applications of this are through eyeglasses. When we look at things, we have a near point, the point that we can focus an object with our eye. Our eye is a lens itself. And the closest distance at which the eye can typically focus is about 25 centimeters. Again, that's the average. And the furthest distance at which the eye can typically focus, which we call the far point, is usually infinity. It's, we can focus on the stars, we can focus on the horizon, which is an infinite distance away. However, some people's eyes don't operate quite like a normal person's will. For instance, they might be nearsighted or farsighted. Now, the technical names here for nearsighted is myopia, and farsighted, the technical name is hyperopia. Now, a nearsighted person can only focus on close objects. Distant objects become a little blurry. The reason is because the eye is too long or the curvature is too great. And so a diverging lens will fix this problem. Let's look a little bit at what's going on here. So here's your eye, and here's the lens at the front of your eye. The light coming in should focus at the back retina, on the back of the eye. However, for people that are nearsighted, for faraway objects, the light is focusing a little too soon. So it's really focusing here, but it needs to focus back on the edge of the eye. And so what happens is, what we do is we are going to put a diverging lens here to spread the light out before it reaches the eye, the lens of the eye, I should say. And that will allow it then to focus on the right spot. So the lens is too thick, and so therefore we need to use a diverging lens to make the light go to the back retina. In other words, the eye muscles simply cannot relax enough to see faraway objects. As we look at up-close objects, our muscles are working extra hard. And that's why you get tired, your eyes get tired as you read for a long time, because the book is up close. So Well, what happens then is that with nearsighted people, they simply can't relax their eyes to see far away objects. For a far-sighted person, they can only focus on distant objects, but if the object is too close, they can't get a clear picture. This is because the eye is too short, the curvature is too small. A converging lens will fix this problem. So again, if we look at what's going on here, here's the eye with the lens, and the incoming light is focusing too far away. We can't contract the muscles enough when we're reading a book to make it focus on the retina. This is a problem that usually happens with older people. Their muscle is just not strong enough anymore as you age to make it focus on the retina. So you need to wear reading glasses, and reading glasses are going to be a converging lens. So it just helps focus it a little sooner. So the light comes in a little bit before it hits the lens and then focuses on the correct point on the retina. So again, we can fix our vision, or correct our vision, I should say, by either using diverging lenses if you're nearsighted, or converging lenses if you are farsighted. Now, the way that we are going to figure out where the image is actually located, so for the eye, we say that the image is not located at the right spot. To actually calculate where the image is going to be located, our first method that we're going to look at is a ray tracing method. It's going to be a graphical method. So this ray tracing method allows you to find the image placement for a thin lens by drawing things to scale. So we're going to draw 3 rays, and where the rays intersect, that's going to be where the image is located. So we can see a diagram of how this will look down below. So first we'll draw the lens, then we'll draw what we call the principal axis. This is simply a central line perpendicular to the lens. And then to scale, we draw an arrow for our object. So we have 3 rays that we draw. We write in where the focal lengths are. And the focal lengths are always measured from the center of the lens. Same as the object distance is always from the center of the lens. The first ray that we draw it goes parallel to that principal axis. And then when it hits the center of the lens, we draw that line through the focal point. The second ray does the opposite. We draw the line through the focal point on the left-hand side, and wherever it hits the lens, the center of the lens, we draw a line parallel to the principal axis. The third ray goes right through the center of the lens. It just continues on in a straight line. Wherever those 3 intersect, that is where our image is located, so we draw a second arrow, which is going to be perpendicular to the principal axis and intersects with those 3 lines. Notice here that the image is upside down. So just like the lens in your eye, it creates an upside down image in this case. So all the images on your retina are actually upside down. Your brain then knows that it's upside down and flips it back upright. So again, we can use these thin lenses to correct vision. We can figure out where the image is located through the ray tracing method. And so we'll do some problems there with the ray tracing method, and then we'll look at a mathematical method later on. But first, we're going to focus on the graphical method, the ray tracing method.